Okay, so my name is Maïli Kossé. I'm a first year PhD working at the CEA. My PhD director are Paul Loubert and Grégory Jeunesse. And today I'm going to talk about our latest study on superunicity of hydrate in LaH10. Okay, so as you know, high pressure promotes the formation of the novel polar hydrates with unusually high hydrogen to metal ratio called superhydrates. And the system LaH10, sorry, this one exemplifies the properties of these novel hydrogen-rich compounds, which form a novel class of superconducting materials. So we show here another remarkable property for superhydrates, which is superunicity, hydride superunicity in LaH10, sorry, at high temperatures. So for this, we launched ab initio molecular dynamic simulation using the code ABINIT at high temperatures between 1000 Kelvin and 3000 Kelvin. And here is an example of the superunicity in the compound LaH10. So in blue, you have the lanthanum, and in white, you have the hydrogen. And so we followed the trajectory of 3 hydrogen in green, yellow, and red. So you can see very clearly that they diffuse. There's a high diffusion of hydrogen here. And so superunicity, in short, is the diffusion of a sublattice like a liquid. Meanwhile, the other sublattice here, the lanthanum, remains solid-like. So, in order to precise their superunicity, there are two qualitative criteria, which is we need a high diffusion coefficient, which is derived from the mean square displacement we've calculated from the dynamic molecular simulations. We then trace the Arrhenius plot, the logarithm of the diffusion coefficient, and we have a line. And then we also calculated the ionic conductivity. And so we have both criteria, meaning that we have very high diffusive coefficient for hydrogen and high ionic superunicity, very high ionic conductivity, sorry. So it means that the LaH10, sorry, enters a superunic phase at about 1500 Kelvin. And another beautiful results of this study is that the hydrogen doesn't diffuse randomly. They diffuse on the Claertart sublattice. So here there are the hydrogen density probability for different temperatures. At 600 Kelvin, there's no superunicity. The hydrogen doesn't diffuse, and we can see that the density of hydrogen is placed on the sites, the Claertart sublattice. And when it becomes superunic at 500 Kelvin, the hydrogen stays on the same place, and at 2500 Kelvin, the Clairaut sublattice of hydrogen is still there. There's an endurance of the hydrogen sublattice, and when the compound melts at 3000 Kelvin, you can see that the hydrogen density is completely random, it diffuses completely like a liquid. And yes, if you want more details, I will be glad to.
Yeah, on the poster.
Yes,
the poster
to present
section.
it to you
Don't
on the
spoil
poster.
them too much.
That's it.
Okay. Thank you. Thank you very much. The next one is Dario Daghero. Non ti vedo, ecco. Sì, credo che sia ancora.
Okay. I'm here to present the poster. It will be poster number 2 in tomorrow's session. It is about the ionic gating driven intercalation of an organic ion into MoS2, which is molybdenum bisulfide. Well, the technique is the ionic technique, ionic gating technique. It has been used in the past 12 years actually to reversibly tune the charge density, or if you prefer, to shift the Fermi level in various materials. This is a picture that depicts more or less a setup. It's essentially a field effect transistor in which you have a material under study. And here you have a ionic liquid, which is an electrolyte, and the gate electrode. When you apply the gate potential difference between the gate and the material under study, the ions in the electrolyte migrate and create an accumulation of charge that is, of course, reversible in the sense that when you remove the gate voltage, the accumulation of charge disappears. Actually, by properly choosing the ionic liquid, it is possible to use the same setup also to induce a non-reversible, so a permanent change in the properties by intercalation of something. For example, by using this kind of ionic liquid, which is called MnBF4, it is possible to induce the intercalation with the hydrogen. And this is what we did in a single crystal of MoS2. And this is the setup. So this is the ionic liquid. This is the counter electrode, which is actually the gate. We apply the potential difference and we measure the resistivity of the sample while applying the gate voltage. So this is the result. This is the gate voltage as a function of time. First, we started from 0, then we made a ramp up to 3.5, and then we kept it constant. And the resistivity of the sample first did not change, then decreases a little, and then made a big jump to a value which is about 3 orders of magnitude smaller than the initial one. And then when we just disconnected the gate terminals without removing the sample from the liquid, the resistivity started to increase again. So, and then saturated. Clearly, this means that something happens during the gate that is volatile, but something remains. And how can we control the final doping? Well, we can't, but the only thing we can do is to remove the sample. For example, here, we just remove the sample from the bath, we clean it, and we can measure it, and so on. And it turns out that whatever happens inside the gate is permanent. So the crystals are no longer similar to the previous ones, and this is the resistivity as a function of the release time, which is the time after the disconnection of the gate in which the sample remains inside the bath. So what has happened? We thought to intercalate hydrogen, but this is not the case because, first of all, the samples retain the 2H crystal structure, but what is inside is actually the MM, so it is the cation of the ionic liquid. And indeed, you see that this is the spectrum, the infrared spectroscopy spectrum of MoS2. There is nothing. This is the spectrum of the ionic liquid, and this is the material after intercalation. You see that it has exactly the same peaks. Does this make anything about the in terms of electronics? Yes, of course, because we see that there is a shift in the Fermi level by using Kelvin probe microscopy. All the details are on the poster. We can determine that there is actually an upward shift of the Fermi level by 175 million volts. So we are actually doping with electrons. And what happens to the resistivity, to transport properties? Well, the pristine sample is, of course, an insulator. And by choosing the release time, we can go to higher and higher dopings. And what happens is that we are here, smaller doping, increase the doping, increase the doping, increase the doping, and increase the doping. So the most doped sample is then the black one, okay? So first of all, we see these humps that are suggestive of the existence of a charge density wave order. And indeed, if we plot the resistivity, the derivative of the resistivity as a function of temperature, we can extract the temperature of formation of this charge density wave, which is decreasing, actually, which is increasing with doping. And moreover, there is actually a sort of decrease first and then increase again of the low temperature resistivity, which is suggestive of a sort of re-entrant metal to insulator transition. What are the possible causes of these two behaviors will be discussed in front of the poster. Thank you very much, which is number 2. Okay.
Okay, the next one is Philip D. Okay. I tried to. Let me see if it works. Okay. 5 minutes.
Okay. Hello, everybody. I'm Philip D. I'm a postdoc working with Peter Hirschfeld and Richard Hienig at the University of Florida. And I have to admit, after seeing sort of the heroic ab initio efforts going on at this conference, I do feel like this is sort of an odd topic. But if you are at all interested in the Migdal-Eliashberg formalism, perhaps this could be an interesting topic to you. So the idea is that in the Migdal-Eliashberg formalism, there is a primary approximation, which is Migdal's approximation, sometimes referred to kind of tenuously as Migdal's theorem. And for a long time, people have been interested in what happens when you add corrections to this theory. And so a paper that kind of intrigued me and some of my collaborators more recently was this one by Schrödi et al., which said that using a bare electron phonon coupling, they were able to use vertex-corrected Eliashberg theory to find unconventional pairing symmetries. And I just wanted to say that, when we looked at this problem, I realized there was a lot of literature of people looking at these corrective studies. And so this is not exhaustive, but just enough that I could fit on one slide. So there's a lot of people that have been talking about vertex corrections, but not many of them have ever said you could get unconventional pairing. So if just a quick refresher, what is the Migdal's approximation? It basically says that in the electron self-energy with a simple electron-phonon interaction, the main term that we might keep to describe electron-phonon vertex is just this first-order diagram. In this next higher-order diagram is usually neglected, and that kind of gets rid of all the crossing diagrams that look like this. And Migdal's argument was basically that you have a nice adiabatic system where the lattice moves a lot slower than the electrons, and this combination of the adiabatic ratio and the electron-phonon coupling should be small for this approximation to work. So in Schrödi et al., they set up the problem quite nicely, and they wanted to solve the Eliashberg equations for some simple Holstein model, but they included some material specifics, namely a bunch of unconventional superconductors simply projected into the problem using an effective tight binding picture to capture the nested Fermi surface in each of those materials. So there's a cuprate, iron-based, and a heavy fermion superconductor. And they get these unconventional pairing symmetries. including a D-wave pairing symmetry. So we said, okay, let's assume what they did was correct. Adding this first vertex correction in a self-consistent way gives you potentially unconventional pairing. Do you see this with all of the diagrams included? And how do you include all the diagrams? Well, okay, in an implicit way, a Monte Carlo simulation does this. And so we looked at their parameters, and effectively so far, we don't see any leading D-wave pairing symmetries. And so we looked at their parameters. They didn't specify what the filling was, but more or less we were able to test sort of in the ballpark of where they were. So largely what we find is that if any sort of instability wins, it's going to be a charge density wave for their parameters. And so this is kind of intriguing. This is sort of part one, which I'll present on the poster. And part two, which I'm not talking about this conference, is can I reproduce their results and explain why a vertex corrected Elie-Ashberg theory can give you those results if we are able to reproduce them, among other questions. So that's it. If you're interested, come see the poster.
The charge density wave successibility is the charge successibility at such finite Q.
Yes.
Okay.
Yeah, I guess I had an extra slide with the resulting charge density wave correlation function, but you can see that.
And the next one, sorry, is Federico Giannessi. Non ho capito perché qui.
Good evening, everyone. I am Federico Giannessi, and in my poster, I will present a way to optimize the efficiency of prediction of novel ternary hydrides. So we are at the end of the first day of this beautiful conference. So hydrides have been described better than I ever could, but they are basically hydrogen-rich compounds that we like because they show high TC superconductive behavior in high pressure conditions. So in the few years since the discovery of SH3 in a superconductive state, pretty much the whole binary hydride space has been completely explored. So the next logical step is to explore the ternary hydride space, which presents a few issues. The first is the sheer amounts of possible combinations. We go from 117 possible binary hydrides to over 6,000 possible ternary hydrides. And the second issue is simply the amount of enthalpy calculation necessary to obtain a more or less precise, accurate convex hull. So in our work, we tested two hypotheses. The first is that to obtain a real convex hull, we can approximate it with a convex hull obtained by a set of templates or prototype structures. And the second is that there is a correlation between the depths of the binary convex hull associated to the edges of a ternary convex hull that guarantees the presence of ternary stable compounds. If you want to know more, come to the poster session tomorrow. We got wine and cheese as well, so that's it.
Thank you. The next one is Moritz Gubler. Not here. Okay, so we can pass to Paolo Ingelido. Ingelido o Ingelido? Ingelido. Ti vedi? No. No.
Good afternoon, everyone. I'm Paolo Ingelido, a master's student of Sapienza University of Rome. And now I'm presenting my project, Ab initio estimate of kinetic stability in superhydrates, supervised by Simone Di Cataldo and Lilia Boeri. We propose a method to include kinetic effects in the evaluation of the range of stability the range of stability of metastable structure. And we are focused especially on superhydrates because they are potentially room temperature superconductors. And the kinetic effects are, as Christoph Heil said in his talk, are very important to give a more rigorous limit for synthesability of the compounds. And for this reason, we want to evaluate the lifetime of the metastable structures, because in most papers published so far, we use the dynamical stability to determine the range of stability of metastable structures, but we want to extend these methods, include the consideration about the lifetime of these structures. And we have shown in our group, Lucrezzi, Di Cataldo, and Heil, that an improper inclusion of these kinetic effects increase the predicted stabilization pressure of a new ITC barium silicon H8. So these effects could be explained, the misleading between experiment and predicted results. And evaluating lifetime of metastable structures required to find the minimum energy path, but the minimum energy path is determining the best minimum energy path is quite difficult. So we use these two methods, the structure mapping and the pathway optimization, to define the best path which matches the two structures, the endpoints. And the structure mapping algorithm finds the best mapping between the two structures. So it aims to find the best overlap between the unit cell and to find the best mapping between atoms, minimize the distances in real space of atoms and the dissociation of chemical bonds. With the variable cell nudge elastic band method, we optimize the pathway, and in this method, a set of images connecting the two endpoints that are relaxed through which you have forces that are some of the physical forces and the spring forces that connect the two images. And I want to show you some results and conclusion. We apply these methods to the transition between CCM phase and R3M phase in HS3. And I want to show you that an optimal choice of the initial gas, so the applying this mapping, reduce the barrier to 3.5 electron volt per atom to 0.3. And this is the first step to obtain a good initial gas, and so the real minimum energy path. And for this reason, we are interested to other superhydrates, especially where the superhydrates where there is a misleading between experiments and predicted results. Thank you for attention, and see you tomorrow at the poster session.
Thank you. We can move to the next one. There is Subhasish Mandal, not here. Antonella Menino.
So hi everybody, tomorrow I will speak about ab initio study of possible metastable occupation of tetrahedral size in palladium hydride compounds. Today, I will just give you an introduction about the topic. So if you want more results, please come tomorrow and we can speak more in details about the study. So as you know, recently, many hydras have been studied, especially at very high pressure. So the challenge now is to reduce the pressure. So all the study that I'm doing is at ambient condition. We know that the palladium hydride in his full octahedral configuration has been studied yet, but what I want to do with this work is to basically study other configuration of this, other possible configuration of these palladium hydride compounds. So basically, what I did was to choose randomly some configuration. So we know that the hydrogen can stay in an octahedral size or in a tetrahedral one. Here in this slide, in the non-relaxed, in this figure here, in which there is written non-relaxed, we have that the hydrogen in octahedral configuration are colored in red. Instead, the hydrogen in the tetrahedral configuration are colored in green. So basically, I classify many of those structures according to the number of tetrahedral and octahedral size that they occupy. And then I relax using different methods. I use two different semi-classical methods, one in which I didn't change the shape of the cell, and the other one in which I changed the shape of the cell. And then I want to compare those results with the one that I obtained using the stochastic self-consistent harmonic approximation. Basically, what I want to explain you more in detail tomorrow is the difference in the structure compared to the other methods, and also the changing in the structure first of all, and of course this affects only the electron-phonon interaction, so the critical temperature for those kind of compounds. So thank you for your attention, and if you are interested, come tomorrow. Thank you.
One is Cesare Tresca.
Good evening, I'm Cesare Tresca from CNR SPIN. I speak about the prediction of ambient pressure superconductivity in ternary palladium copper hydrates. Also in this case, we try to slow down the pressure needed to superconduct. We start from an experiment performed in 1974, in which Strisker, alloying palladium hydrate with noble metals, registered the increasing of superconducting critical temperature up to the maximum in palladium copper hydrate, in which the superconducting critical temperature was the double with respect to palladium hydrate, with a concentration of 50% and a hydrogen on metal ratio about 0.7. We are speaking about ambient pressure superconductivity. So we perform a theoretical density functional theory on the palladium copper hydrates in low and high hydrogen content. So starting from the palladium copper alloy, we start with the low hydrogen content. We were able to predict all the structural parameters that are in literature. Hydrogen acts like an electron donor, and from the dynamical, we studied also the dynamical properties that are characterized by the presence of a gap between low energy metal modes and high energy hydrogen modes in analogical experiments. We estimate the electron phonon coupling and the critical temperature that is below 1K. So this is not the phase we are searching for. We move to the high hydrogen content in palladium copper dehydrates. The doping of the hydrogen is still present. And from the dynamical point of view, we see that at the harmonic level, we have some instability, dynamical instability that we studied it in the adiabatic way following the relative eigenvector. And from the study of the energy profile, we can conclude that those positions are the equilibrium position for hydrogen, dynamically stabilized. We noticed that now the gap is absent, and this produce an higher electron phonon coupling that now is 0.9 with a critical temperature of 45 K. Of course, in this kind of compounds, the harmonic effects are important, as demonstrated for palladium hydrate and so on. So we try to estimate the contribution, to mimic the contribution of anharmonic effects, applying a low pressure to this structure, able to dynamically stabilize the structure. Of course, there is a decreasing of the electron phonon coupling and on the critical temperature. But probably this is the phase realized by Strisker. So in conclusion, we studied the ternary palladium copper hydrates, probably understanding what happens in the Strisker experiment, and we hope that this study will motivate a re-examination of this experiment. Thank you for your attention, and thanks to the collaborators.